So we're now going to talk about how the Java parallel streams framework maps the tasks to be performed onto the common fork join pool. And I had some fun revising this lesson over the weekend by using my good friend ChatGPT and Claude. I'll tell you why I had to use Claude for some of the analysis that we're going to talk about here. So recall that in the common fork join pool, each worker thread sits there and basically runs a loop that continuously scans for work to do. And the idea is to try to keep everything humming along, keep the cores maximally utilized. In this particular example, we don't care about anything other than tasks that are associated with parallel streams. We don't care about other kind of tasks, although if there were other tasks using the common fork join pool, they would also use the mechanisms we're describing. But all we care about here is parallel streams. Again, we want to keep things humming along and keep them doing as much work as they can. Recall internally there's a double-ended queue called a deck that each worker thread in the pool uses to get the tasks it's going to work on. And basically what happens is the parallel streams framework, when it has a stream like this, will create fork join tasks that will be run by worker threads in the common fork join pool. And remember the following, this example sort of illustrates this a bit. Remember how in the common fork, in any fork join pool, any parallel stream, the way things work is the computations are done left to right, top to bottom. So for each element that is in the input, we're going to run all the computation operations, the intermediate operations, for that element. And then those things are going to be collected together or reduced or whatever we're doing in order to be able to get the final result. So just keep that in mind when we look at the example. So here is the code, or at least a snippet of the code, from the Java parallel streams framework that performs the execution of these tasks. And it's called AbstractTask. It's in Java util stream. You can get this code. It's all available in open source form. This is the version in Java 8. I looked, and the version in Java 19 is essentially the same. So the AbstractTask superclass is used to implement most fork join tasks in the Java parallel streams framework. It's a superclass, which means it's customized for different kinds of entities. It's customized particularly for different kinds of terminal operations. There's some that are for the so-called reduce operations, which, as you recall, are run to completion operations like reduce and collect. There's also other things in there for the find operations, which are short-circuiting terminal operations. There's also things in there for the match operations, which are also short-circuiting. So there's a bunch of different kinds of subclasses of AbstractTask. And the AbstractTask, especially the part we're going to look at here in the compute method, manages the splitting logic, the tracking of the child tasks, intermediate processing, and the notification of final results to something called a counted completer that will pull all the parts together and try to come up with the final result. So because AbstractTask extends task, it implements a compute method. And you can see here, this is going to be a non-recursive task. It's more like a recursive action because it doesn't have a return value that comes back from compute. And we'll see why that is later. So the compute method decides whether to split a task further and or compute it directly. That's kind of one of the things it does. And the first thing it does, it comes in and it sets up some local variables, and then it goes into a while loop. And you can see here, it will repeatedly call try split on the input source that it's been given until there's nothing left to split. So every time it calls try split, if it gets a non-null back, it'll execute the body of the loop, which we're going to look at in a second. However, when it gets a null back, that says, OK, we're done. Now go ahead and do the rest of the processing. So the task to fork is a parameter k. And if we were to go look at the actual signature for AbstractTask, you would see that the parameter k itself is an abstract task. So what this is basically doing is this is creating a tree of abstract tasks, which are going to be scheduled to be run in the common fork join pool. So it's going to make a whole tree of these things. And what's interesting here is every time through this loop, it checks a flag called fork right. And every time it checks this, it switches back and forth between forking right false versus forking right true. And the reason behind this is they want to only fork things, well, they want to alternate forking so that if the splitterator is a biased splitterator, like we saw for linked list, where it doesn't have even-sized chunks, you won't have a tree that's like super long on one end and very short on the other, because that would make less effective use of the processors in the common fork join pool. So it goes back and forth doing this, and it also makes the appropriate child, and then it's going to fork one of them. So whichever, either the left side is going to be forked or the right side. Remember, when something's forked, it's placed, that task is placed onto the deck in the calling thread, and then it's available to be stolen by other threads in the common fork join pool. So it'll fork one of the things, and then it's going to continue processing the other child in the loop. So it's going to loop back around again and then split the side that it didn't fork. So it's going to keep doing that. And again, the idea is to try to make this balanced tree of tasks. After it's done splitting, now we've got everything chunked up into little chunks which have a size of 1, typically. And then what happens is, after try split returns null, we drop out of the loop, and then the task, whatever task we're dealing with at this point, we call its do leaf method. And this method can be overridden. This is basically a hook method that's overridden by different subclasses of AbstractTask. But for the reduce operations like collect and reduce, that will typically call for each remaining, which will then process all the elements sequentially at that point by calling try advance. So that's actually going to walk through, and what it's going to do is going to take the input element it has, and it's going to run it through all the various intermediate operations that are part of that particular stream. And it's going to run all that sequentially. And that's going to return a result of some kind, and that result is going to be set as the task's result. So after we compute the value of the task, it's set as the result of the task. And then the final thing that happens here as the method completes or finishes is the try complete method is called. And the try complete method is a call on the counted completer. And try complete will check to see if all the processing is done for all the things that are running in parallel. And if so, it will then notify the parent up the tree in order to be able to start the process of merging everything or joining everything together to have the final single reduced result, which will be the result at the top of the tree. Super complicated stuff. Surprisingly, alarmingly few comments. They would get a bad, if the people who wrote this code would get a bad score in this class because they didn't comment their code at all. However, the good news is when you take this code and you give it to an LLM, plus some other context, it will start explaining what it's doing. And I learned, interestingly enough, the size of AbstractTask is large enough to fit within the default context window of ChatGPT-4. Some of the other files, however, that are part of the streams package are too big to fit in the context window of ChatGPT-4. In particular, there's one called reduceOps, which handles the operations that do run to completion reduction, like collect and reduce. So I had to cut and paste those into Claude, which has a much larger context window, and get it to do the analysis there. So it was really fun, and a good way to, one of the things that LLMs are typically pretty good at, if you give them enough context, if they have enough context window, is being able to summarize code. So it was able to give me a pretty good explanation of what it was doing. So after all of this stuff gets done, every time something calls fork, in this example we just saw back over here, that fork is stuck on the head of the worker thread's deck, and then when it's either going to be stolen or it's going to run at some point, and each worker thread processes its deck in LIFO order once it's finished doing all the looping stuff we saw. And when it's popped off from the head of the deck, it's run to completion. The LIFO order improves locality of reference and cache performance. And then it steals, if there's more stuff that can be dealt with on one thread and it doesn't have anything else to do on another thread, then the idle thread or the about to be idle thread will steal work at the tail of busy threads' decks. And the reason for doing that, as we've talked about before, is that because we're typically starting out with a whole source, then we split it in half, push it on. We take those things, divide them in half, push them on. Stuff at the end of the deck or the tail of the deck are going to be larger units to work on. And therefore, we get this nice recursive decomposition because we have a lot of stuff to work on. We take that, we split it further and further and further. So parallel streams push larger chunks onto the deck before processing smaller chunks, which is exactly what you want because you get maximized utilization of parallel processing with multiple cores. So that's the end of the discussion of parallel streams internals. You don't have to know all these details in order to program with parallel streams effectively. You might have to know some of these details to do well in the next quiz, but you don't have to know all these details to program with it. But I do think it's kind of interesting to see how it works under the hood and the amount of effort they went to try to make all this stuff work in a nice, clean, seamless way, such that you can program to the parallel streams functional facade, and they can handle all that gobbledygook of mapping and splitting and applying and combining and so on in the underlying parallel infrastructure. If there was no parallel streams framework, you could get the same effect, but you would have to be the one to do all that splitting and merging yourself, which is what you could do if you chose to program with the common fork join pool minus parallel streams. But there's really no need to do that anymore.